Superconductors are materials that conduct electricity with zero resistance when cooled below a characteristic temperature. Also, these materials expel magnetic fields when transitioning to the superconducting state. A normal conductor can become a superconductor when the electrons are paired to cooperate with a material's vibrating atom. The phenomenon of superconductivity was discovered in 1911 by Camerling Ons. Superconductors find applications ranging from MRI machines and practical accelerator to magnetically leviated trains. Ongoing research focuses on raising the operating temperature and developing new high-temperature superconductor materials for various objectives. History of superconductivity. One of the most intriguing quantum phenomena, superconductivity, was first discovered in 1911. The major milestone in the scientific understanding of superconductors are as follows. 1911, superconductivity was first experimentally observed in mercury by Dutch physicist Heike Kamerlingh Ons. It vanished electrical resistance at 4.2 Kelvin temperature. 1933, the Meissner effect explained the expulsion of magnetic fields from superconductors' interiors. 1957, Bardeen, Cooper and Schrieffer formulated the BCS theory, successfully modeling superconductivity in conventional low-temperature superconductors through electron-photon interactions. 1962, Brian Josephson predicted the tunneling of electrons pairs between superconductors separated by an insulating barrier. This Josephson effect enabled the design of ultra-sensitive magnetometers. 1986, George Bednorz and Alex Muller discovered new ceramic oxide superconductors with remarkably high critical temperatures exceeding liquid nitrogen temperatures. 1987, yttrium, barium, copper oxide ceramic materials was discovered with a superconducting transition temperature of 93 Kelvin, which is above liquid nitrogen 77 Kelvin boiling point. 2008, iron-based temperature superconductors were discovered, further expanding the large of material exhibiting this phenomenon. Principle of superconductivity. Conventional superconductivity is explained by the formation of electron pairs known as Cooper pairs combined with electron-photon interaction as conceptualized in the BCS theory. Cooper pairs at sufficiently low cryogenic temperatures, interaction between conducting electrons and crystal lattice vibration phonons cause the lattice to distort slightly. This causes some electrons near the Fermi level to become unstable and rearrange into pairs called Cooper pairs. These Cooper electron pairs can move through the metallic crystal lattice without resistance, as they do not get scattered by the lattice vibrations. Large-scale coherent movement of many such tightly bound Cooper pairs leads to exactly zero DC electrical resistance inside the material. The Cooper pairs also induce a weak superconductivity in the rest of material lattice, further reinforcing the effect through a feedback loop. Meissner effect. The Meissner effect leads to the complete expulsion of external magnetic flux lines from a superconductor's interior when cooled below the transition temperature. This distinguishes superconductors from other types of conductors. Superconducting materials. Different classes of materials exhibit superconductivity at different characteristic temperatures. Some that have achieved the highest known superconducting critical temperature are types of superconductors. Superconductors can be broadly classified based on their transition temperature and material properties into low temperature and high temperature variants. Low temperature superconductors, these include elemental superconducting metals like aluminium, lead and mercury, which exhibit superconductivity just a few degrees above absolute zero temperature. These also include weak, low capacity superconducting alloys made using niobium, titanium and niobium tin with transition temperatures well below 30 Kelvin. LTS is explained well by the BCS theory, which models the electron-phonon interactions. High temperature superconductors. These are made using complex ceramics compounds such as YbCO and BsCCO, which incredibly show superconducting transition at temperature between 77 to 138 Kelvin. These do not require electron-phonon interaction and Cooper pairing and follow unconventional mechanism arising from their crystalline lattice structure. They offer higher current carrying capacities and magnetic field tolerance compared to LTS. Also, they simplify cooling requirement drastically. Unconventional superconductors. These are also being researched carbon-based organic compounds, metallic hydrogen, that become superconducting upon specific doping or under extreme pressures. Applications of superconductors. Some major application areas and benefits of superconductors are: challenges with superconductors. Some major technical and economic challenges exist in harnessing superconductors for practical applications. High operating temperatures. Superconductors face challenges in achieving high critical temperature as conventional superconductors require extremely low temperatures. Researchers are developing high temperature superconductors like cuprate superconductors like YbCO, which can operate at higher temperatures such as -181 degrees Celsius. Fabrication and scalability. Superconducting materials face challenges in fabrication and scalability due to complex manufacturing processes like thin film deposition and wire fabrication can be expensive and time consuming, especially for high quality wires using materials like REBCO. Material defects and stability. Superconductors are sensitive to defects, impurities and structural instability, which can degrade their properties and reduce critical current density. Researchers are exploring ways to mitigate these challenges through defect engineering and material stability improvement. Cost and commercialization. Superconductors, particularly high temperature ones, can be costly to produce and commercialize due to raw materials, fabrication techniques, and cryogenic cooling systems. However, advancement in manufacturing processes and cost-effective production methods are being pursued to overcome these challenges. Integration and compatibility. Superconductors can be integrated into existing systems, requiring careful consideration of electrical insulation, thermal management, and mechanical stability to ensure compatibility with other materials and technologies. Superconductors in India. India has proactively furthered superconductivity research and development with noteworthy indigenous contributions. National Superconductivity Mission. It was launched in 2017 by the government to develop indigenous superconductors and their application in various industries, focusing on fundamental research, advanced materials, collaboration, technology transfer, and creating a skilled workforce. Local manufacturing of MRI machine. Indian scientists have successfully built the country's first MRI machine superconducting magnet domestically. This aligns with national self-reliance goal in high-end medical equipment. Nuclear fusion program. Subsystems for fusion reactors relying on superconductivity are being developed locally via initiatives like the Steady State Superconducting Tokamak. High temperature superconducting transformer. BHEL has indigenously developed India's first transformer using cutting-edge high-temperature superconductor technology through R&D efforts. International collaboration. Indian institutes are engaged with CERN for the Particle Physics Project PIP second, focusing on designing novel superconductivity and room temperature magnets.